Good evening, everyone. Good evening, everyone. Yeah, I know. Can All right. Good evening, everyone. Welcome along to Cafe Scientifique. My name is Scott McIndoe, and I'm the host for the chemistry talks at these events. And it's my great pleasure tonight to introduce my colleague, Heather Buckley. Heather is an associate professor, recently promoted. Well done, Heather. In the Department of Civil Engineering at UVic, of course. Like the superstar she is, she's also Associate Director of CamTech, which is the biggest research center on the campus. So Heather is a chemist by training. She's a engineer by profession now, being in the Department of Civil Engineering. She got a PhD in inorganic chemistry at the University of Berkeley. And she now runs a laboratory at UVic dedicated to developing new sustainable green technologies with the goal of improving human and environmental health. Heather is also something of an adventurer. Sometimes she and I have reason to exchange our experiences of our most recent weekend. And Heather has always done something unusually epic. She has done either climbed a mountain or skied down it, or she's been windsurfing on Lake Nitinat, or she's been at Burning Man doing whatever people do at Burning Man, which someday she will tell me about, I'm sure. Okay, so I am very pleased and excited to be welcoming Heather here. She is going to talk tonight about some of the science that she's doing in empowering communities through interventions at all stages of the drinking water supply chain. Take it away, Heather.
All right, thank you so much, Scott, and thank you everyone for being here. I'm really excited to be here tonight. As Scott told you, I've been here in Victoria. I've been here for about 4.5 years now. And I have this incredible honor and privilege of getting to work with this phenomenal team of graduate, undergraduate, high school, and postdoctoral researchers here at the University of Victoria. And I get to teach 3 different courses that are focused around water and drinking water quality, as well as getting to teach first-year chemistry, which is great because I get to convince all of them that they should study water, which is the coolest thing ever, so they should all do that. I also am really incredibly privileged to wake up every day here on Lekwungen territory, to live, work, and play on these unceded lands, and to have the opportunity to play in the waters here, the waters of the Cowichan tribes, the waters of the Pacheedaht Nation, and the waters of the Dididat Nation. And I just feel so blessed to be existing in these spaces and have exposure to the many different ways of knowledge that come with living in these lands and living and working in these waters. So I've spent my entire life really, in a lot of ways, learning through the lens of a scientist, and so I feel really lucky to now have these many other lenses and many other experiences that I get to share. So as Scott also mentioned, I'm trained as a chemist. So in some ways, from a research and practice side, my formal part of my water journey really started after I finished graduate school. So I suddenly found myself with the power vested in me by the regents of the University of California in this position where I could say things and make choices and talk about the choices that we're making as humans, and how we should show up in the world, and people would listen to me. I mean, Look at this. You're all sitting here listening intently. We've got folks on the live stream listening, and you're not even getting bonus credit for the quiz at the end. So thanks for being here. I also want to send a huge shout out of thank you to all the folks on the live stream and wish a happy 42nd anniversary to my parents who are joining us today from Calgary, Alberta, from Canmore, Alberta, rather. I'm going to hear about that later. So while I was at the University of California, I got really involved in the green chemistry movement. And so in the context of green chemistry, what we're really thinking about is designing and choosing chemicals and materials and processes and doing that in a way that propagates the notion that we should do that in ways that minimize harm and maximize benefit to all peoples and to the environment, and that we do that throughout the entire life cycle. And we consider that in our choices, in our actions, and in our results. So I decided that it was really important for me to take that knowledge and paradigm and everything I'd been developing during my education and apply that to the problem and the practice and the solutions that we use around water. And I did this because I realized in all of the communities that I encounter that everyone has a water story. So there are a few things about water that have really made it resonate with me throughout the context of my work and through that paradigm of green chemistry. The biggest thing with that is that water is fundamentally non-replaceable. It's the one chemical in all of our processes and in all of our solutions that we just can't get rid of and can't move away from. When we think about making our chemistry more sustainable, there's a lot of things that we can do where we can replace hazards, we can replace non-renewables. If we imagine rebuilding this building that we're here in tonight, a really lovely old building in downtown Victoria, we could think about using sustainable lumber. We could think about novel composite materials from renewable sources. We could look about carbon capture derived cement. We could choose different fibers in the furniture. We could insulate differently. We could put solar panels on the roof. There's so many of these things where we could substitute our current processes, our current products. But at the end of the day, we would still need to have the same water that we're using, the water that's making the beverages that you drink, the water that's made the food you prepare, the water that's running in the bathroom so you can wash your hands properly after you use the toilet and not spread the results of your going to the bathroom into your food. An important part of the water journey for all of us. We need water for all of these things, and we need water to live. So the universality of water, the way that it shows up in all of these places, leads us to another key feature. We think about water scarcity and water challenges on a global scale. We still have more than 10% of the global population doesn't have access to safe drinking water. But with that being true, and with close to 50% of the population experiencing water scarcity at some point during the year, we also end up with in a space where water is also a very local experience, and it's a very personal experience. So we start to see climate change showing up a little bit more concretely in our lives, and in many ways that's becoming more real every year. We have a pretty solid consensus now that climate change is human activity derived as the primary driver. And so that's still really big, scary, nebulous, feels like something we can't always do something about in our day-to-day lives that will have that impact. And it can be very indistinct. The questions, who benefits, who's harmed, who's responsible, as we come up with solutions and try to find ways to bring this together in a better way, are complex. So I'll ask, out of the audience, has anyone recently brought up the climate crisis in a gathering, a family community event? Awesome, yes. Who else is talking about climate with your family, with your community, over Mother's Day brunch, any of those things? Awesome. And how did that go? Did anyone have consensus at the table? Lots of people did. I'm seeing some thumbs down. Some of these conversations are still really challenging, and shout out to you and hold you up for having those conversations, even when they're difficult conversations. If you have one of those conversations and you found everyone did agree, reach out, branch out, find people who are still struggling, have those conversations in more diverse communities, and bring people into the story and understanding. And one of the ways that you can do that is that you can bring in stories of water. Because while climate doesn't necessarily feel real to everyone in the big scale, everyone has a water story. So what sets water apart And what makes water special to me is that personalness, is that fact that everyone's got this water story. We've got crops that failed due to drought. We've got that canoeing trip when you were a kid, where you had to portage amid black flies because there was dangerously high water. You had that cow that floated away in the 2001 floods in Regina. Was anyone there for that? That was an interesting time. But the cow was miraculously unharmed. The doula who hiked 5 miles in the 1997 Victoria snowstorm. Was anyone here for that snowstorm? And delivered your nephew. And your nephew's now all grown up and doing amazing things in the world. The summer at the lake where you fell off the dock and fell in love. Watering your tomatoes 5 times a day last year during the heat dome. How many people kept tomatoes alive during the heat dome last year? How many people tried really hard and lost some of their tomatoes last year during the heat dome? Yeah, lost the zucchinis. Zucchinis survive everything, but not last summer. The glacier from your childhood. Used to be an easy walk. Now it's a long hike up to that glacier because it's a lot smaller than it used to be. Your best friend carrying her cat's kennel on her head, evacuating the floods in your hometown. Again. Your grandmother's walk to school up a hill, both ways in the snow. Rivers, floods, droughts, storms. Water flows through all of our lives because everyone has a water story. So I'm going to share a bit of mine. So I grew up on Treaty 7 territory in Niitsitapi in Alberta, where the junction of the Bow and the Elbow rivers has attracted white settlers to build a fort that grew up to be the city of Calgary. I knew only a little bit of the smattering of the relationships of the Kainai, Siksika, Piikani, Stoney Nakoda, and Tsuut'ina with these rivers and the others in the area. That wasn't a lot of the story that we heard when we were growing up in the city. I do know that many of the dams on our rivers really changed both the landscape and the lives of the people who lived on and in and beside those waterways. I was very aware growing up, though, of how proud we were as a city of our water. Our little oil boom town that had rivers that ran high and fast in the spring and cold. The mineral richness meant we had the best water in the world, and I had no idea that soap is supposed to sud. I also grew up proud of our ability to conserve water. In summer, we watered the raspberries at 6 a.m. The grass was always crispy brown before stampede. We turned off the tap when we were brushing our teeth. I learned in university that kids growing up in BC didn't learn to do that, and I was flabbergasted. Winter storms sometimes closed our schools. Another part of my water story, being out with the neighbors, shoveling out cars, clearing the snow off the trees, saving those branches from breaking under the heavy weight of a big snowstorm. And then 3 days later, because it was Calgary, everything would have melted, and we would be out in our boots fishing icebergs out of the gutters, and a microcosm of what was going on in our raging rivers that could not figure out what was going on because our water story kept changing from solid to liquid and back again over and over every winter. So, unlike a lot of kids on the Canadian prairies, I also grew up on the water. So I started sailing when I was 3 years old on the bow of my dad's laser, and then on little wooden optimists that we built, and like a good 6-year-old, I helped build them. And I saved for university teaching sailing, working on the Glenmore Reservoir, which is the city of Calgary's drinking supply. So growing up in a place where water was so scarce and every drop of water needed to be used for multiple things, it never really occurred to me as unusual that we would be recreating on our city's drinking supply. But it did just seem normal and natural that, of course, we couldn't swim, you couldn't pee in the water. We weren't allowed motorboats. And so in 6 years of teaching sailing, I never actually learned how to drive a motorboat, but I can rescue another boat from a boat because we learned that dexterity instead, because that was what we did to keep our water safe, but be able to use our water over and over again. Our work was directly affected by the river system, so we were very aware of what was happening with the storms and the floods in the spring, all the way from the glaciers up at the top down to the Mississippi, which is what the Bow and Elbow ultimately flow into. For the water operators in Calgary, in days where computer modeling was nowhere near what it is now, had the daunting task of predicting what would happen upstream with the the storms and the spring floods, releasing enough water to protect the crops in Saskatchewan, while meanwhile saving enough water that we would have something to drink through the whole summer. And some years they succeeded, and it never ran dry, but some years we sat on docks that were completely washed up on the mud because the river was so low because the storm never came through. So in June 2005 came the first of a pair of 100-year floods that rocked our city in a decade, a common story around 100-year floods in the time of climate change. And despite draining the entire reservoir, there was more water spilled over the top of the dam uncontrolled. It damaged 40,000 homes, obliterated crops for hundreds of kilometers downstream. The wooden break wall that held up our friendly little public boatyard was destroyed. The boatyard was completely gutted and became a mass of mud and broken boats. It was good that we were young and strong that week, because there were a lot of boats and a lot of mud to lift. So 8 years later, thousands of miles away in Washington, D.C., the heartbreaking and back-breaking floods came again. And come hell or high water, the people of my first home came together again. By that time, I had a lot more perspective, a lot more knowledge of what this climate crisis meant and what this water story meant for our community, and also an understanding of the privilege that brought the capacity we had for resilience in my first home. Because in Calgary, much like in Victoria, it's one of the few places in the world where the wealthy live along the waterfront. In most of the world, this resilience doesn't exist because the riverbanks are inhabited by the poor and marginalized. And when these floods come more and more often, more years than not in many places, they start over again. So after 6 years, after all of that sailing on the drinking supply, which is unimaginable in Victoria, but is how many parts of the world make water work for us, spent 6 years in Vancouver in Musqueam territory with more water than we possibly knew what to do with. I moved to California to Ohlone territory. I was there for the last normal winter before we had a decade of drought. And so in Berkeley, I learned to take 3-minute showers. I learned to shower into a bucket, to only flush number 2 using that recycled water. A whole nother level of conservation that we'd never considered even living in the dryness of Calgary. And with my life increasingly tied to the water and the tides with windsurfing, as Scott mentioned, knowing the tides, knowing what the storms would mean for water quality in the bay, where it would and wouldn't be safe to swim, what towns' water quality would suffer the most as a result, and whose homes would be washed away and roads washed out if a king tide happened to coincide with a winter storm. I also learned that even though it was amazing, living in that sunshine every day almost for a decade, it was very, very stressful, and we carried a lot of weight in our parched home, wondering when day 0 would come, and watching the reservoirs drop every day. So we would breathe a little easier when there were rare storms came through, even though we knew that they were too soon or too short or too intense. We were still, as Garbage would say, only happy when it rains. So at the end of a PhD, 5 years in California, making these beautiful, amazing, highly air-sensitive molecules that in and of themselves have nothing to do with water. They are a different water story I can tell of doing work where you exclude all of the water or everything breaks. So working in that contrast to everything else. I found myself trying to find the right way to connect my green chemistry universe to solve global challenges. So I'd gone to Berkeley hoping to solve the platinum problem in fuel cells, a major environmental justice challenge, also a water challenge that one of my amazing group members has actually taken on, which is pretty exciting to hear about, but I didn't have a good path forward. But during my PhD, I'd spent time in Jordan, India for green chemistry, spent time in the foothills of the Himalayas, back home in the Rockies, in Georgian Bay at the site of Canada's last side-launch shipyard, and in the eastern Sierra Nevadas, seeing some of the water reclamation and restoration projects that were happening in places like Mono Lake. Learning as well about stories of feminized fish from pesticides dumped into waterways, cancer clusters from industrial pollution in places like Sault Ste. Marie. And that kept connecting me back to the realities of the combination of climate crisis and human activities. And in all of these, the common thread was that with all of these challenges, everyone had a water story. So when I worked in Ahmedabad in India, our factory would shut down anytime the water wasn't turned on for its 2 hours in the morning. How did the workers feed their families that night? What happened when the same disruptions happened in the informal settlements that some of them lived in? What was their water story? My work at the Berkeley Center for Green Chemistry and then at the National Lab in Berkeley created space where I finally found the place to intersect my chemistry story and my water story. So at Berkeley, we worked on safer alternative preservatives for home and personal care products. This started creating space for people to ask the question that was the tagline for tonight, the question of what is in my water? And to realize that we can all be part of that solution, that we can design and we can choose safer chemicals for products that we put on our bodies and in our homes, and ultimately those products that we put down the drain. So at the National Lab, we started to answer the question, what's in my water? By developing water treatment technologies to help remove contamination from groundwater that was being used as an alternative to surface waters that were bringing people acute contamination, and starting to really understand then the difference between things in our water that will harm us today and things in our water that will harm us in the long term, and realizing that as we think about water and quality of life, both of those are really important things in our stories. So in this question, what's in my water, is, as I said, and as prompted you to join us here tonight, that's where our water stories, all of your water stories and my water story meet here today. Because everyone here is coming from a watershed. It might be from Bowker Creek, one of our nearest watersheds. It might be the Padma, the Meghna, the Rhine, the Amazon, the Elbow, the Congo. And everyone here has a story from their watershed. So, another question for all of you. How many people have wondered at some point, hey, what's in my water? Great. Well, you've come to the right place. How many people, when you were making your coffee this morning, thought about the question, what's in my water? How many people needed to have coffee before they could form a coherent sentence in their brain? That is totally fair. So then, how many people, after you started drinking your coffee, started thinking, what's in my water? All right. So one of the great luxuries we have living here in Victoria, there are a few complex situations, exceptions to this, and buildings that have challenges with water quality. But it is that in general, our water quality here is absolutely phenomenal. We get to think very, very little about it day to day. It is okay that you didn't think about your water quality before coffee this morning. That means that there are some civil engineers out there doing their job. So good job to the civil engineers who are keeping our water clean. It also means that we as a society, largely, we are making our job easy for civil engineers because as a community in Victoria, we've had the privilege, but also taken the initiative over the last 100 or so years to be able to protect our watershed in a way that means that we do almost nothing to treat our water in Victoria. Our water comes down from the Sioux Reservoir in the Goldstream watershed. And the leach water supply is also one that's protected from development for future use. And those decisions were made 100+ years back in many cases. And that means that we all get to benefit from the ecosystem services of these undisturbed watersheds where we don't allow things that would harm us to get into our water. And so the ecosystem naturally does that job for us. And then that means that when we pipe water down from those reservoirs, before we put it in the pipes, in case it ends up sitting somewhere for a couple days, we add a very minimal amount of chlorine, but we don't do a whole lot else to our water. And we can do that and be safe because we have that privilege, but also because as a collection of cities, we have made that choice to prioritize protecting those watersheds over economic development in a lot of cases. And the long-term result is huge and powerful and beneficial. So an interesting side effect of this is that if we compare our water to, say, the water that folks are drinking in Jerusalem or in Baja California Sur, there's actually a lot more stuff in our water than there is in the water in those locations, because water in those locations is treated by reverse osmosis desalination, which removes everything. It's okay that there's a little bit more stuff in our water. The extra stuff that's in our water is benign, and we're going to talk more about that stuff and give it some more specific names than stuff, although it's pretty fun to say that over and over as well. But yeah, I'll talk more about that as we go along, but yeah, that is an interesting and important difference, that if people who come from different locations drink that water, they might think our water tastes funny, but I mean, we all know we have the best water in the world. But in Calgary, we also all know we have the best water in the world. So, yeah. So, another question. At some point in your life, how many of you have lived or worked in a place where the water was not safe to drink? Yeah. Okay, so a few people where it's been not safe to drink. Anyone who's lived somewhere where it was technically safe but not pleasant to drink? Yeah? All right. So when you lived in those locations, what did you drink? Beer. Yes. Bottled water. Tea. Yes. So the water was boiled before you drank it and then turned into tea. Yeah, those are all great options. If you're a visitor in those locations, were you in places where the locals maybe did drink the water? Yeah, so there was often that difference and that privilege, one in terms of locals may be able to drink it safely because of being habituated to it, but also that as visitors, we often inhabit spaces with privilege where we can afford to continually buy water or to find it from other sources. So what was it in that water that made it, what did it taste like, smell like, what made it unsafe? Sulfur and rotten eggs, yeah. A lot of well water in Alberta from outside the cities. You get a lot of that as well. Any other contamination folks knew about? It was brackish, too much salt in the water, absolutely. So that's something that in the short term is safe, but if you spend your whole life drinking brackish water, you end up with elevated salt and that causes heart disease problems. So all of the work you're doing to eat a careful low salt diet, as I can see you all with those French fries out there, can be undermined if your water has too much salt in it. So in some cases, you could smell the water, you could see the water, it looked absolutely terrible. Yeah, you could get phenols as well, absolutely. And sometimes the water that you knew you shouldn't be drinking looked and smelled and tasted, if you got some in your mouth, perfectly fine. And this is super normal. This speaks to different types of water contamination. And since we have all of these different types of contamination, what that means is deciding whether or not water is safe, deciding what's in water isn't super straightforward. So we need different methods of detecting them. So in general, we've got 3 major categories of contaminants that we talk about. Looking over at my samples, we're going to start passing around samples here, and the folks in the front row are going to get involved in participation, whether they like it or not. Don't worry, there's no dolphin splash zone or anything. I'm not going to throw water all over you. There's no you must be this tall to ride this ride. I mean, if you want, I can dump my water samples on you after. I hear some disappointment over on the side here. Some of them I won't dump on anyone, but most of them are completely safe. You can add them to your drink if you want. You never know what it may taste like. All right, so we've got these 3 categories of contamination. I'm going to walk us through them. I'm going to ask if you would like to participate. I will actually ask for your consent if you want to be involved in analyzing this water, but hopefully folks will want to get involved. I'm not going to ask anyone to drink any of them, although you could if you wanted to. All right, so I've got a few samples of water here, and I am going to hand them down to the folks in the front row, and other people can maybe see them. I don't know how well they're projected, but I'm going to hand these down to the folks in the front row to pass around, and you can let me know what you think about them. Also, I'm going to do the thing where I take the mic off so I can walk around and trip over things. It's going to be great. All right, you guys want to have a look at these and pass them around and maybe see what's going on there a little bit? All right, does anyone want to tell me what do you see in these samples?
Sediment.
All right, we've got some sediment in them. What else do we see in the samples?
Over that one. Okay. Discoloration, or it looks discolored.
Yeah, we've got some discoloration in one of them. It kind of looks like urine. So it's not urine. I didn't bring any urine samples because if it gets opened by accident, I will tell you afterwards what they actually are. What do you think? Would you want to drink any of those? Not really. They don't look super great to drink, do they? Yeah. So there's a whole bunch of different things going on in these waters, different types of contaminants. You can pass them around for folks to have a look. And what we see is that one of the things that's common here, folks said they saw particles, they saw that they were maybe cloudy, they couldn't see very well. Maybe it was discolored, looks like it had urine in it, which, as I said, I promise it doesn't. I'm not handing her. I will actually say everything in those samples is food safe. Please don't open them, but if you do, nothing will happen. So the cloudiness of the water, which is one of the things that comes up looking at these, sometimes there's big chunky particles that folks will see in them, and sometimes there's, you can't really distinguish the particles, but you also can't see it. So we call that turbidity when it's cloudy and you can't quite see through it. And turbidity is a good measure of how much stuff is in the water, how much stuff that doesn't quite dissolve but stays suspended. So it turns out, as is the case with these samples, is that having dirt or other stuff in your water in and of itself doesn't actually cause any safety problems. But it can make it smell or taste funny. If you open those samples, you'd probably find that they all smelled or tasted a little different. And I made them up today, so they would be fine to drink, but you might not want to leave them to sit for a while because who knows what would happen to the organic materials in those if they sat for a week. So if you were expecting them to taste like tap water, though, they taste kind of different. As I said, if you travel to Calgary right now, you think, man, that water tastes weird. And when people from Calgary, my sister was here last week, they're like, why does your water taste so weird? Because everyone's water is different. So as I mentioned, we definitely had the best water in Canada and Calgary, and nobody seemed to have magnesium deficiencies, interestingly enough. So what we see in all of these samples, this turbidity, and the other interesting thing we see here is just handing you these samples, you were all able to analyze these. You were able to tell me something is up with this water just by looking at it with your eyes, which is pretty cool because as a group here in the front row, we just had a small crowdsourced spectrometer. And it was a very effective spectrometer that correctly identified that one of these samples only had water in it and the other 3 samples all had something else in it that did not look good. So do people want to know what's actually in them? Okay. So the one that looks like urine has a little bit of soy sauce. The one that looks like bits of stuff is tea bag, an opened up tea bag after the tea had already been steeped out of it. And the last one is a tiny bit of hot chocolate powder. So all of those that look super awful and terrible, 100% safe to drink. Soy sauce one might taste a little funny. The hot chocolate one I wouldn't drink after 48 hours because there's milk powder in hot chocolate and that would just get gross at room temperature. But right now it probably just tastes like really dilute hot chocolate, like the stuff you get at the hockey game. Yeah, maybe a little worse than that. But we were able, by looking at those, to see, okay, there's a measurable amount of stuff in here, and we have instruments that really easily do that. We can measure turbidity of a sample, even at a level where you wouldn't quite be able to see that cloudiness with your own eyes. We are able to see that using that kind of meter in order to distinguish between samples that have more or less stuff in them. And so that's really useful to us because is that still working? It is. Great. So that's really useful to us because even though having the stuff in there is inherently completely harmless, it does end up coming to play in our second type of contamination that we'll talk about, which is a type of contamination that I did not bring to share samples of tonight because you're all eating dinner, which is also why I won't talk about poop, which is microbial contamination. So when I talk about this with elementary school students, the correct term for microbial contamination is OMG, it's alive. So we can call it that, or we can use big fancy science words just for the sake of it. So as I said, there's a couple reasons we're not going to do an analysis of microbes tonight. As I said, you're eating dinner. The other one is that unlike looking at the particles in water, we aren't necessarily immediately able to see how many microbes there are there. And even with scientific tools, if we pick up a sample that has bacteria in it, potentially at levels that are dangerous to be able to consume, we are not able to just take that water and measure it directly. We actually have to do something to the water first in order to take the samples and multiply it up enough to be able to see. So what we do is we take a water sample. If you're anywhere close to thinking about drinking about it, it doesn't have that much bacteria in it, but it has a little bit. And so we need to take them, we need to multiply them. So what do we do to create conditions for bacteria to multiply? So bacteria are actually a lot like humans, and if they're not feeling good, we can give them things to make them feel better. So when you were a kid, what did your parents feed you if you were sick and they wanted you to feel better? Cod liver oil. Oh, that's a new one I hadn't thought of. I don't know if we give our microbes cod liver oil, but we might. I heard ginger ale. Yeah, sugary liquid. What else did people have growing up? Chicken soup. Yeah, something with some protein and some salt in it, and it's nice and warm. And I heard something else. Rye. That might be is that a generational thing? I can't see. I can't see who gave that answer, but that was not something I was ever given in my childhood when I wasn't feeling well. But some microbes might be into it. Sure, absolutely. So we've got these different contexts. We've got the broth from chicken soup. The other big one that I always had growing up was Jell-O. Yeah, yummy, delicious, sugary, bright colors, makes your tongue turn rather blue or whatever color it is. You keep pretending you're sick so you can have more of it. Ice cream, yeah, another great source of protein and fat and sugar. So we take our microbes and we make them feel better. We make them warm and cozy, and we wrap an incubator around them, and we give them lots of salt and sugar and water. And they're like, hey, this is great. And so they multiply, and they multiply, and they multiply, and they multiply until we have enough of them. And what we do is we do this for exactly 24 hours or a set length of time. But for our example, we do it for exactly 24 hours with all of them. And then after 24 hours, they've multiplied to the point that we can see them on the Jell-O, or we can count them in the chicken soup, and we can count exactly how many of them there are. And then we extrapolate that back to know how many there were before we gave them all of our fun, delicious things to eat. And doing that multiplication, unfortunately, we can't do that in the course of an hour here. Also, I was told that we're not supposed to set up biosafety level 2 labs on the stage. So, minor details. So my research group is busily doing that right now, which also means they've put things in to incubate, and they've gone home for the night. And tomorrow morning, we'll know how many bacteria there were in that water sample. So they get really good at counting. So if you're got kids or grandkids, any of them annoyed by learning to count, just tell them that they need to do it because they might grow up to become a microbiology PhD student one day. And then you have to count all those colonies. Actually, we mostly have instruments that do it now, but we train the undergrads to do it by hand so they understand. They understand the suffering of their forebears. So when we do this part, when we're looking at water, there's all kinds of different microbes in water, but we actually typically, what we will do is we'll culture our good friend E. coli. So E. coli tends to get a bad rap, so it's worth me pointing out to you that most E. coli is actually benign. We think about it as being this big, horrible microbe, but it's actually mostly pretty mellow. And so the reason that we count E. coli is not because it's the one causing the problems, but because it is a good indicator of fecal contamination. So I think I said I wouldn't talk about poop. I was actually lying. I'm going to talk about poop here for a second. So E. coli comes out in wastewater, so it comes from your poop, and if it gets into a water supply or from other organisms, it is an indicator that other contamination from wastewater is there. And that's one of the biggest risks to safety of humans drinking water, is if there's contamination from other human poop or from other animal poop. And so we take the E. coli. E. coli is really well behaved. It does the experiment that I just described really smoothly. Oh, thank you. Nobody drank them. Oh my goodness. Maybe I shouldn't have said what they were quite as soon. I should have told people they were fancy cocktails with really high proof alcohol, and then people would be trying sniffs. Anyway, so when we're culturing our E. coli, the E. coli is pretty benign. It responds really well to our Jell-O and chicken soup. It lets us count it, so it lets us know really readily how much is in there. And so that lets us do a comparison of how much bacteria is in our known sample versus how much is in the sample we just collected, and we can have a really good sense of what we have in our water and whether it hits a threshold of being safe enough for us to drink. So now if I pull these two back together, this is going to be a part that's a little bit stay with me. But so we take the cloudy water, we take the clear water. It's clear, but it's secretly poopy. We pull them together. And these contaminants are totally unrelated in where they came from. The hot chocolate powder has nothing to do with the poop. But they're related in treatment. This part's a little bit subtle because it's the presence of the hot chocolate powder affects how easy it is to kill the E. coli. So when we kill bacteria, we usually do it with bleach. And we know how much bacteria we have. We use bleach or chlorine are the two ways you'll hear about water being chlorinated, same thing basically. When we know how much bacteria we have, because we did that Jello test, we know how much chlorine we need in order to kill them back down to a safe level, so below about 500 microbes per milliliter. That's a super normal level. Your body can readily handle 500 microbes per milliliter in drinking water. That's the upper limit of what's allowed to leave the water treatment plant. And then we add a safety factor, just in case the water sits around for a bit. And then that means that any new bacteria that do start growing get killed off pretty quickly. But the catch is, if there's stuff in the water, if there's turbidity, other organic matter in that water, then the new bacteria that are there have that as nutrition, and additionally, all of that turbidity, the extra stuff in the water, also reacts with chlorine, and it starts to eat the chlorine up. So, quick question: has anyone gone backpacking? Awesome, yeah. Has anyone used Aqua tabs or drops to treat your water when you're backpacking? Yeah. So you know when you read the instructions, it says if your water is super cold or if it's cloudy, you use twice as much treatment. Folks have seen that before? Yep, awesome. This is why. It's because if your water is cloudy, it means it has other stuff. It has turbidity. It has organic matter in it, and that's going to react with some of the chlorine. And so you need to add a bunch of extra chlorine so that you can have that reaction and still have some left over to kill your bacteria and get your water safe to drink. Yeah, the cold part is about the rate of the reaction killing the bacteria versus how fast the chlorine forms and will bubble out of the water. And so it's making sure that you have enough of it to have a fast enough reaction before your chlorine level drops. That's a great question. Yeah, so the cold part also plays an important role there. So there's always going to be some amount of organic matter in our water, and that has to be accounted for. I mean, especially in the water here in Victoria, it's coming straight down off the Souk watershed, and we're not doing much to it. So there's that little bit of organic matter there, and that's totally fine. So the standard 0.5 gram per liter, so 500 milligrams per liter is the acceptable drinking standard. That keeps the water tasting normal. It keeps the amount of chlorine we need to deal with bacteria down to a very minimal level in a place like Victoria. And it also limits how much material there is in there that could have side reactions with chlorine. So you may have heard of the concept of disinfection byproducts. So if there's a lot of organic matter in your water and you chlorinate it, you can end up turning that super benign organic matter into things that are chlorinated that might be carcinogens. So if we keep our level of organic matter in our water really low in the first place, we don't add much chlorine, we don't generate carcinogens, our water stays safe and happy, and we don't get diarrheal disease because we killed the bacteria, and we don't end up getting cancer in the long term because we've kept those other contaminants out. So in summary, if we limit the amount of organic matter in our water, we can limit our chlorine use, we can still remove our pathogens, keep our water safe to drink. So I told you there were 3 major types of contaminants we could test for. The first one, the organic matter, the dirt, that was pretty easy. We tested for that right here. Second one was a little more complicated, so I described it but did not set up an entire microbial facility here for your viewing pleasure. So if anyone comes up to campus, then we've got space there, and I've got really cool grad students who love to talk about their work as well. And that's another. And so the second one, that microbial growth prevention, that is a big part of what we do in our research. We put a lot of effort actually in getting away from the chlorination. So we work a lot on making antimicrobial surfaces that you can shine light on them, and they will prevent microbial growth through the interaction with visible light, and I'm working on alternative chemistries that we can use right in the drinking water as well. So I'd love to have conversations about those with folks as well. But I did promise I would talk about what was in our water. And so one of the questions that always comes up with that is, so I've got water in my house, I've got water in my well, I want to get it tested. What do I do about that? So can I just show up at UVic and knock on your door, Heather, and be like, hey, hey, can your grad students test my water? I mean, my grad students are super badass. So there's a really good chance that while we're sitting here talking, they're secretly developing like X-ray vision to instantly count bacteria, and this whole culturing thing I'm telling you is now a lie. But assuming they haven't done that and that they're actually enjoying the evening and taking time off, which I'd like them to do in the evenings, I'm sure they'd also love to talk about that. The reality is that it's a lot better rather than bringing something to a research lab where we have a lot of new things going on but not regulated testing. Actually taking your stuff to a certified testing lab is really the way to go. So I looked into this a little bit because I was curious how it works on the island. I've kind of known where it worked elsewhere. And in this context, what ends up happening is these home testing kits, they'll be a lot like a pregnancy kit or a COVID test kit. So we've now gone into a world where basically everyone has used a testing kit that's pretty similar to something you would use to home test water. And when you home test your water, you don't have to stick anything up your nose. So you can do that with a home testing kit. You can send things to a certified lab. And the reason that certified labs and home testing kits are so much more effective than my super cool, amazing grad students is they're all set up with calibration. So the reason that this calibration is important is that every sample needs to be measured against a whole set of standards. A certified lab already has a set of standards that they have set up ready to run your sample and thousands of others in a day. And so they can take those samples, run it through, and they've got a whole battery of tests. So they can test for a bunch of different metals, which is where we're going next. They can test for different microbes. They can test your turbidity, and they can give you results that are also useful. So if you've got well water, Island Health recommends that you test every 6 months for bacteria. Does anyone here have a well? Or have friends who have a well? Used to have a well. Awesome. All right, so if you've got a well, or if you've got friends who have a well, or out on the islands, the islands, a lot of those are on well, on the little islands. You want to be testing every 6 months for bacteria, every 3 to 5 years for chemical contaminants, and if you do any major work, then you want to be testing a little more often as well. If you dig a hole right next to your well, it might affect your well water, test your well in extra time. So living here in CRD, the lab you'd be sending your stuff to is CRD Laboratory Services. They've got a great website. If you're ever like, I can't find their website, send me an email, I'll help you find their website. But yeah, that's what you're doing if you've got well water. If you've got tap water, generally if you're testing your tap water, because that's regulated at the city level, if you're concerned about things within your own home, like maybe you've got some old pipes and you want to know if you've got lead contamination, that's a really great, important question to be asking if you think you might have problems from your pipes. You generally have to do that privately, but there are a bunch of companies that do it. Island Waterworks is one of them that I found that seems to know what they're doing. I haven't sent a sample to them. I feel pretty lucky. Our house seems to have good water, but yeah, there's lots of good options for that. So if you're like, I want to know what's specifically in my water, I can't tell you by just looking at it. I mean, unless your water looks like that, if it looks like any of those three, you probably shouldn't drink it. Even if it's just soy sauce. If there's soy sauce coming out of your tap, you're doing it wrong. So I alluded there very briefly to metals and other contaminants, which brings me to my third type of contamination I want to talk about tonight. So this one is in some ways fundamentally different from the first two, because in general, it doesn't affect taste, it doesn't affect smell, it doesn't affect how we feel when we're drinking our water, sometimes doesn't affect us for months or years afterwards. Trace contamination from chemicals typically leads to chronic rather than acute effects on our health, which means it's the sort of thing that shows up many years later. It can also be really challenging to detect because like bacteria, many of these contaminants are at these parts per million or parts per billion concentrations. But unlike bacteria, because we're dealing with elements and not OMG, it's alive, conservation of matter applies. And so there isn't a really good way for us to take a sample of water and just get really, really large amounts of the thing that was in it. So we have to find other ways to look at it. We can't just give it food, clothing, and shelter and let it get big and warm and fuzzy and then count it when it's not looking. So this means that when we're looking at these ions, these atoms, these molecules, we have to find different ways of being able to tell them apart. And we have to be able to tell them apart from each other and from the million or more times more water molecules that they're surrounded by, and from the other stuff that's around that there's 1,000 times more of that's pretty benign, like sodium chloride. There's a tiny bit of sodium chloride in your water, but 1,000 times more than there would be of any of the things you need to worry about. And telling those ions all apart from one another is not easy. So that means we have to take any of these elements or molecules, anything we want to know about, and we have to figure out what is unique about them. And we have to figure out how many of them are, because one of the things that is important to keep in mind with many of these contaminants, not all, but in a lot of cases, the dose does make the poison. So a really small amount of some of our contaminants won't do us any harm, but if we get up above a certain threshold, it starts to cause problems. So to do this, we have a couple really great techniques that we use. And these will let you detect just about anything. One method that's really lovely that we use to separate molecules that might look, to separate these molecules that might look really similar to one another is to separate them out by mass. So mass spectrometry is a major focus of Scott's work. So I'm not going to embarrass myself up here by trying to describe what Scott does in detail. I'll let you ask him instead. But the basic principle, we're able to separate everything out by the ratio of the charge that the ion of it carries and its mass, the mass of that the atom weighs. And we can pass those through a magnetic field, and charges curve as they go through a magnetic field. And so since every element in the periodic table has a different mass, this means that we can separate things out by element and tell them all apart. So there is absolutely nothing wrong with this method. It's a fantastic method. I love it when Scott's group and our group can work together and use this method, except I wanted to demonstrate identifying ions live tonight. And even when I asked Scott really, really nicely, he wouldn't let me borrow his mass spec and put it on my bicycle and come down here. So we're not going to do any mass spec tonight. Just like Scott to ruin a good party. No, Scott actually proposes most of the good parties, so yeah, here we are. Anyway, so instead, since we can't use mass spec, we are going to learn a different method. And honestly, I think this method might be a little more fun in a crowd context. And it's going to illustrate the same idea. So just give me a sec here. Oop, I'm caught on a thing. So I'm just going to come over here, and I promise I'm not doing anything my mother wouldn't let me do in her kitchen. Which is a higher bar than things I would or wouldn't do in my own kitchen, I realized, which is what I was originally going to say. I was like, oh, actually, I do all kinds of crazy stuff in my kitchen, so maybe that's not a great metric. So I'm just going to set that down for a second. Okay. How well are people able to see that flame? A little bit? All right. Okay. It shouldn't be producing any more smoke than the candles on your tables, so I think we'll be okay. That's my strategy anyway. If the smoke detector does go off, then you will all know why. So the thing that we have here that is unique about elements other than their mass is the difference in the energy between their orbitals. So who's heard that word before, orbitals? Yeah, okay, awesome. Folks are comfortable with orbitals. That's great. So it might seem like I'm kind of splitting hairs here. So if I've told you that we can't really look at the sizes of whole atoms very well with our current setup, how is it that I'm going to look at how much space there is between the different orbitals where the different electrons are sitting on the same atom? Like that seems like it would be a harder question to ask than, is this heavy element heavier or lighter than that atom? So the good news is that for some elements, and all the ones we're going to look at here, this difference in energy corresponds to the amount of, corresponds to the wavelength of visible light. And so what that means is that yet again, just like we did with our group up here at the front where we built our first human crowdsourced spectrophotometer, we are going to be able to build another crowdsourced spectrophotometer, this time using everyone in the group in the class. I told you there's a quiz at the end. There might not be. We'll see. It's a pop-un quiz. It might surprise not be a quiz. We'll find out. So the other good news is, yeah, for most folks, the eye is actually really good at detecting visible light. So I'm going to give you a little bit of help, and with that, you're actually going to be able to tell what is in these 3 solutions I've got up here. Put this up here so that I can mostly talk into it, and I'll try not to lose the crowd on the live stream. So what's going to happen here is that we're going to set these ions on fire. I've got 3 different contaminants in these samples of water here that I've got in my little paper test tube rack, and we're going to see the energy jumps happening between the different orbitals. So what we're going to do is we're going to split the room into 2 groups. So I'm going to get everyone here over on the right. You're going to raise your hands if you see a red flame. I'm going to divide right down the middle here. So everyone on the right, you're going to raise your hands if you see a red flame.
We're on the left.
Okay, you're on my right. On the starboard side of the room. How about that? And everyone who is on my left side of the room, on my port side of the room, because we're on the left coast, so maybe that language will work better for folks. If you see a yellow flame, you're going to raise your hands. All right, everyone got that? Okay, this side, what color are you raising your hands for? Red. This side, what color are you raising your hands for? Yellow. Fantastic. Okay, is there anyone here who's colorblind? All right, so we've got someone who's colorblind. Fantastic. I have a very important job for you. So I do not want you to go along with the crowd nearest you who all have this weird color vision thing going on that makes them less able to see some of the subtleties in intensity of light. Instead, you probably have fewer cones and more rods, depending on the type of color blindness, and you can see light better at low levels, which is super cool. So what I need you to do is I need you to raise your hand every time you see a flame, regardless of what color it is. Got that? Awesome. Okay, let's give this a try and see what happens. Awesome. Red and yes, perfect. Okay. Awesome. We got red, we got yellow. Yeah, red. Nice. There is a much more violent way I can do this, but I didn't want to risk setting off the smoke detectors. Okay. All right. Yellow, you got it. Yellow to stick around for a little bit longer. That's fun. Let that burn off. Still yellow. Why aren't your hands up? There we go. See? Your spectrophotometer. Anytime there's yellow, you need to be letting the world know. Yeah, a little bit of red. The red's not behaving quite as well. There we go. Yep. That one's kind of yellow, but it's kind of not. Yeah, so you'll notice there. So we had a pretty clear indication when we had red. Red team had it with a pretty clear indication when we had yellow. Our one errant spectrophotometer worked very, very well because the very last sample there, it started out yellow, but then it stopped being yellow. It was something else. And so all the red people were like, well, there's nothing going on. And all the yellow people were like, well, there's nothing going on. So if we'd only been looking for red and yellow, we would have been like, oh, well, that water's clean. There's nothing in it. I don't see red, I don't see yellow. But thankfully, we had a multi-purpose spectrophotometer within our crowdsourcing that was able to tell us, yeah, there's still something in there. And that's actually super important because of the 3 things that I was testing there, that very last color, that pink color, was coming from potassium, which is a lot more likely. We need to know a lot more about how much potassium is in water when we're dealing with it from a safety perspective than the others. So the red color, let's see if Yes, people are still putting their hands up. Awesome. People who put their hands up there, you get an A+. Congratulations. So the red color that we saw there, that was lithium. The yellow color is caused by sodium. And then that pinky purple color that I know all of you actually saw, but that only one of our photon detectors saw, that was potassium. So what we've done here as a group with all of these different reporters, every time you put up your hand, if we built an actual spectrophotometer, there would be a point on the detector that is flagging and sending an electrical signal into the computer saying, I saw something red. And if only one of the pixels did that, the computer would filter it out and say, oh, that was just errant noise, unless it was built to be really sensitive. But because a whole bunch did, the computer's like, hey, it's red. There must be lithium in there. Let's tell the human at the other end that there's lithium, and they can decide what they want to do about it. And the same thing with the sodium. A whole bunch of pixels said, hey, there's sodium. We need to tell the human at the other end that there's sodium so we can do something about it. And then we had our one lone pixel saying, hey, there's also something here at the end. This is important too. Because it was one lone pixel and it's a pixel and it's small, it used a very high-pitched voice. Although our actual pixel has a perfectly normal voice. Yeah, we'll do that one more time. There we go. Okay. Yeah, so we get those different colors, and then I'm going to do this one once, and then I'm going to do this once, and then I'm going to put the flame out. So that, yes, good job. Bonus marks at the back. All right. So it was really important to have a diverse spectrophotometer there. We could see lithium, we could see sodium. We were looking for other things, so we knew, even though we didn't necessarily know what it was, we knew something was in there. Our detector went off. So that was super useful. So there's actually a lot of potassium in this water, so it's a really good thing that we know about that. That is, out of all these samples, this is the one you actually shouldn't drink. So it's a good thing we know that. So I'm going to put this fire out. It just needs to burn off. Trust me, I'm a chemistry professor. So you guys are remarkably well behaved considering I was just setting things on fire. One of the things I've learned in 5 years of teaching first year chemistry is that, and maybe Scott, you're better at this. Maybe this crowd's been primed by you, and so they know that after fire you can pay attention again. When I teach first year chemistry, after you set things on fire, the class is basically over. So you just can't get the class back under control. They're all like, oh, it's even worse when you explode, or even worse or better when you explode things. Which in a big chemistry classroom you can do, but again, I wasn't really sure about this ceiling. So I always leave those sorts of things to near the end when I am when I'm telling a chemistry story, whether it's a class chemistry story, whether it's bringing folks together like this. So I won't talk too much more having shared this with you, but I do want to kind of bring us back to think about the pieces of this water story. So the water story that I've shared tonight, I've talked a bit about my own story and then about the story of understanding our contaminants in water. So we see turbidity and things that are inherently benign but change the way that our water looks and feels and tastes. We see microbial growth. And microbes can cause a lot of harm. They can also be benign, but to study them, we have a fair bit. We have some good methods to grow them up in Jell-O and chicken soup and make it so we can see when they're there so that we know what to do and how to treat them. And then finally, we've got inorganic contaminants, things that we can light on fire, and we can look right into the inside of the atoms and look at their orbitals. And by seeing those wavelengths and those brightly colored lights when we light those elements on fire, we can tell what's there. And again, by knowing what all of things are that are there in our water, that puts us in a place where we're empowered to make decisions and do things about treating that water. And that's true in our context here in Victoria, where generally we're working with water that is pretty safe. There's not much in our water, and it's a very safe water to drink. And that's also true when we start working with communities around the world. It turns out there are a lot of communities where it is also not realistic to pick up Scott's mass spectrometer and bring it halfway around the world to measure things. And so we develop methods, maybe not something quite as quite as bright and spectacular as lighting things on fire, but methods like that that let us test water in contexts where we can't use those large-scale instruments. So I hope, thinking about that, I hope with all of those pieces, this has been a fun opportunity for all of you. Think a little bit about what's in the water here, what's in the water we played with, what are the watersheds that you come from, and what the stories are that come with those. To think about the water we drink in Victoria, and also the ways that we apply our science and our engineering and pull those together to understand what's in our water. And then at the very end of that, the importance of using those to empower us in design decisions and empower us to design chemicals, design infrastructure, and design our lives. And keep in mind that this water that we're playing with, that we're living among, that we're using, is irreplaceable. And so I'll leave you with that reminder that all of you have a water story, and what's yours?
Heather, thank you so much. What a wonderful water story. And I'm sure many of you have questions. So what I'm going to do is I will field the questions. Heather, I'm going to repeat them and then before you answer them.
Perfect. That way the folks on the live stream can hear them too.
Exactly.
Great.
Yeah. So questions. Yes, please.
You don't have to watch much television before you've seen a lot of commercials for a variety of water purification products. Am I to conclude that I should not take a franchise selling those things in Victoria?
I suppose, oh, sorry.
So the question is about water purification products, of which there are many advertised on television. And so do you simply not need them in Victoria?
Yeah, so I would say as a general rule in Victoria, as I said, there's a couple of exceptions. There are particular buildings throughout the city where there are problems with old pipes and things like that. But by and large, yeah, the water quality in Victoria is such that you do not need to be treating your water anyway. You can drink it straight out of the tap. So as far as the as far as providing something that would serve people and increase their quality of lives, no, that's not a franchise that would take out. From a perspective of being able to sell things, I'm sure you have great skills as a business person, but there may be places outside of Victoria where you'd be better situated to do that, where it would create real benefit.
Well, I happen to live in Shawnigan Lake.
Aha. I am not. This person lives in Shawnigan Lake. I'm not an expert on the water quality in Shawnigan Lake. I imagine a lot of it would be on a well-by-well basis, though.
Oh, actually, it's distributed.
Ah, awesome.
Question down here.
Is light being used for the purification of water, like ultraviolet or other frequencies?
Is light being used for the purification of water, ultraviolet or other frequencies?
It is, absolutely. That's a great question. So we do use ultraviolet light can be used directly for killing microbial growth, for disinfection. That is something that is a situation that does rely really heavily on having not too much other organic matter, not too much turbidity in the water, because if you have cloudy water, the light won't penetrate through. But if you have water that is clear but has microbial contamination in it, then yeah, you can definitely use ultraviolet light. And as I mentioned, there's some work in our group and some other really interesting work in other groups around the world, also converting visible light into mechanisms that can kill microbes. So in that case, we actually have molecules that will absorb the visible light, transmit the energy of that into oxygen, making reactive oxygen species, and then those can kill microbes. So those are typically not used for disinfection, but they can be used for cleaning surfaces, for killing growth on surfaces.
Yes, please, at the back there. So you did traveling, and you've visited many places where they've investigated wastewater treatment, and then
Balance of science
Yeah,
versus cost.
Yeah, the balance of science versus cost. Thank you. Sure.
Absolutely. Yeah, that's a great question. So as you said, my core focus isn't in wastewater, but I work with a lot of folks who do wastewater work, and I think there's absolutely a balance between those. I think one of the big questions that often comes up in various contexts, I mean, including in rural contexts in North America, is whether we've got centralized wastewater treatment or whether we've got wastewater treatment that is decentralized either as a septic system, can be a common decentralized method that we'll see a lot of places up island, or in some cases you don't have any kind of wastewater treatment and you'll have just localized latrines or open defecation. I'd say as a general rule, the science for conventional wastewater treatment is pretty well established. We're able to effectively use microbial communities that we grow in the wastewater treatment plants to degrade most of the matter before it's discharged. But I mean, we've even seen this in the city of Victoria, the question of technology versus cost. The technology hasn't changed, but we only got wastewater treatment for most of the city of Victoria about 1.5 years ago. And so that was a decision that was made based on the trade-offs of the cost of doing it, the harm to the environment of discharging untreated wastewater versus the harm of the chemicals and processes needed in the wastewater treatment that also have to do with the size and scale of the city. But yeah, installation of cost, particularly for something that's large and centralized, the upfront cost can be a real barrier, especially for remote and rural communities. Did that kind of get it where you were going with that? Yeah. Awesome. No, for sure.
Yes,
And
please.
if you want to dig more into that, I've got a colleague who does a lot of water and wastewater in international contexts who I'd love to connect you with.
I'm wondering if you could describe your research. I'm assuming you're doing research on alternative green treatment of water. I know you mentioned visible light, but is there any other research that you're doing, let's say as an alternative to chlorination or ultraviolet treatment of water supplies?
Heather, tell us some more about your research.
Thanks. That's a great question. So one of the interesting things that we're working on, one of the major challenges that shows up in the context of basically all types of water treatment is limitations that come from biofouling. And so if you have microbial growth on surfaces, particularly on surfaces for treatment technologies, it will limit the effectiveness. So one that's really particularly shows up for that we work on in our research is in reverse osmosis desalination, which is a method I mentioned is used in a lot of areas that have brackish water. So basically the entire country of Israel, most of Baja California Sur, like 10% of the city of San Diego all get their water from desalination, predominantly reverse osmosis desalination. And a major energy cost in that is the fact that over time, the membranes that are used for water treatment get clogged by microbial growth. And so it's much like if you're trying to wash dishes into your sink and drain your sink and you end up with spinach down in the bottom. It just gets clogged and water doesn't get through very well. And so then the overpressure you need goes up. So the work that we're doing around that is developing chemistries that can go into the feed water, so the water upstream of the membrane, to reduce growth of microbes in that upstream water, but using chemicals that won't damage the membrane, because chlorine will damage the membrane, so it can't be used in that context. But by introducing molecules that will readily break down. So if they do pass through or get out into the environment, then they'll quickly break down into benign components and that prevent microbial growth in the upstream and don't damage the membrane itself. That's one of the major research areas we're working on that directly ties to water treatment.
Yes, please.
Ooh.
What are the pros and cons to fluoride in our water?
Yeah, that's a great question. Thanks for asking that. Because actually, that's one of the areas of research that our group also works on is developing sensors to detect contaminants like fluoride or arsenic in drinking water. So fluoride is one that it's very much a dose makes the poison type of example. So very low levels of fluoride, so up to about 1.5 parts per million of fluoride in your drinking water leads to better health outcomes in terms of dental health. If you get above about 4 parts per million, it can be a little higher if you've got a population that eats enough, that has enough calcium in their diet. But we'll say above about 4 or 5 parts per million, you do start to see it causing weakening of teeth and bones. And the more you have, the more serious it will be. So it's very much at low levels. There's that benefit. And one of the things that often comes up in that context is the balance of that benefit versus if there are other side effects. And one of the biggest arguments, I would say, in favor of fluoride is as a public health intervention. In a context, in a society where we don't have universal access to free dental care, and this shows up even more in the United States in the context where people don't have access to basic health care necessarily. Having something that is an intervention on the community level provides everyone with that baseline level of access to having better quality teeth, which has huge outcomes in terms of other health, because healthy teeth means you don't end up with bacterial infections that end up in the rest of your system. So yeah, that's kind of where that trade-off lands, and it's very much a dose-based thing as well. And typical fluoridation in communities that fluoridate their water typically fluoridate up to 0.4 parts per million.
Yes, please.
Just wondering if you could comment on research or work done for the removal of microplastics in our water. Are we actually that concerned about it because it's so prevalent everywhere else?
Is there work done on the removal of microplastics from water?
Yeah, there absolutely is. And I think that's something that's really, you're absolutely right, that's growing in awareness and prevalence of research around it in the last couple years. I actually had a really great opportunity to do an interview call with a group of 5th graders in Maple Ridge about 5 weeks ago here, and they were working on a project on just understanding microplastics. I guess a lot of what comes up with microplastics, there's kind of two levels of concerns around them. One is the physical bits of material themselves. And when we're dealing with smaller organisms, the ability for them, they can disrupt their growth in a significant way. So the actual physical particles. So in that sense, much like asbestos as a carcinogen in a non-water context is a concern because of its physical form. The other major concern with microplastics is that they will often be places where other hazardous chemistries in the water will tend to accumulate, because many of the hazardous molecules in water will be not super duper polar, and so they will gravitate towards the non-polar plastic material. So then you end up with these things that are concentrated, and then they get eaten by fish or uptaken by algae, and then they start to accumulate and concentrate up in the food chain.
Yes, please. So can you comment on the differences between drinking reverse osmosis water and just normal drinking water?
Yeah, so they taste very different. If you're used to drinking water that has been treated by reverse osmosis, and then you drink water treated by another method, it tastes very strange, and vice versa as well. Are you thinking in terms of the health impacts? If you had a very controlled diet where nothing was coming into your food from other sources, then the lack of minerals in that water would, I imagine, be concerning. I'm certainly not an expert on these health effects, but thinking about it through like all of the other things and nutrients that come into your body through your food, I think that your overall contamination of what you're getting into your body. I mean, if the RO is removing contaminants that are problematic, then obviously that's great. If you've got water that's already safe, like Victoria's water, I think there wouldn't be significant health differences between them because you're not removing anything that would be causing you harm. And in the rest of your food and everything else you're eating, you're going to be getting all of these other constituents. Yes, it removes all ions, non-selectively. Yeah, you're welcome. So sorry, the last question there was, does reverse osmosis remove fluoride? And it does. It removes all ions non-selectively.
Okay, question over here.
Can you provide any insight as to why it is the case that many Indigenous communities that have boil water advisories have gone for so many years despite the strong government commitment to solve the problem, and the problem is not solved?
So why have so many Indigenous communities gone so long with boil water advisories despite the fact the government has declared that this is something that needs to be dealt with?
Yeah, that's a great question. It again goes back to the question we had before about the differential between cost, technology, willpower, cultural context. I definitely can't comment from the perspective of the lived experience of folks living with those boil water advisories. I'm the privilege of being a white scientist living in an urban center. But I do think that there are a few things at play here. One is that there are complexities. There are complexities in contract law and the way that contracts are assigned. There are complexities in public acceptability of technologies when they are implemented, when working in communities where there's a long history of distrust and government abuse. When a technology is introduced that isn't necessarily set up with appropriate consultation with the community, even if it is in principle on the day it's installed the right technology, without appropriate training of operators, without access to equipment to do appropriate repairs when the technology fails, because all water treatment technologies, or nearly all, have some kind of moving parts and need someone actively maintaining them. And so if the mechanisms aren't in place for that, and in some cases a community has just gone for so long being told that their water is safe when it is not, that having a new technology introduced and then being told that that technology is now going to make their water safe doesn't automatically lead to a community feeling they have reason to trust that. And so I think that opportunities to really engage in community consultation and make communities part of the process of treating their water are a big important part of that step forward. Yeah, thank you. Thank you for that question.
All right. Well, we have, Heather's been up here for well over an hour now, so I think we'll call it quits there. But thank you so much for your attention. She will be here immediately afterwards, so please come up and say hi if you want to. And thanks again, Heather, for a wonderful water story tonight. Thank you.